I actually did your course twice, right? So I have another design. I'm not going to show it today, but I really enjoyed the course that I even did it twice.
Yeah, I took that as like just a sign of support because you know that you didn't need to take the course twice to do two designs.
It helps me to be motivated.
Yeah, yeah. Well, yeah. Anyone else listening, you're welcome to like pay for two course tickets, but no, you don't need to.
I think you're doing great. I mean, it's such a great help to community.
Well, thank you for supporting it. Okay, so welcome to another short feedback interview about the Zero to ASIC analog course, and I'm joined today by Ray. How's it going, Ray?
It's going good. How are you?
Yeah, I'm well, thanks. We've known each other for a while. You were on the digital course first, like going back quite a few years now, and you've done a lot of tape outs, including the Z80 and the Atari 2600 recently.
That's true.
Quite a lot of neural processing stuff and accelerators, and now you're doing analog stuff. So maybe you can just give us a little, tell us a little bit about you.
So, yeah, my background is completely software, graphics, actually game development. So I'm completely kind of new to hardware, but it always was like exciting magic. It can, something other people do. And turns out you can do it yourself right now as well. So that's how I got to it. Almost childhood dream, making something.
Yeah. What you always wanted to do, like chip design from childhood, or like electronics in general?
No, I didn't. But I was always like, I was attracted to them in terms of like knowing how they work, using them, but I never thought I can do one. So I never thought even about that.
Yeah, similar story for me. I remember taking apart mechanical things and then later on electronic things, and then there was like the chips on the board, and they were just like, you can't really get inside those or see how they work. So it just was like always a black box for me. So you did the digital course. Why did you want to take the analog course as well?
So my primary interest is neuromorphic hardware, basically somewhere trying to take ideas from biology, which is quite analog, right? There are some elements there of digital, but mostly comparable to digital, but mostly it is an analog thing, right? And we know it's like brain is super energy efficient. So it's interesting to kind of steal those ideas from biology and try to implement them in hardware. And I think in order to do that, you need to know some analog at least.
Yeah. Okay. So what part of the course did you most enjoy?
I actually quite enjoyed the challenge part.
Oh, yeah. Okay. So for people that don't know, there's like the introduction to doing the manual layout is you've got like an obstacle course that you have to kind of solve. And I set a challenge to see who could beat my time, which was about, I think, 3 minutes or something. And Ray, you were the first person to beat him.
Yeah, it's actually, for me, it's like I found it very useful, both fun, but then useful when I had to do my layouts. It kind of, the magic is quite strange software when you come from modern software, right? So it's not hard, it's just that you have to learn it. And I think challenge like that helps to learn it a lot.
Yeah. Yeah, I'm a fan of incorporating fun in things. I think it makes learning easier. What would you say the most valuable part of the course was for you?
The most valuable was, of course, talking to other people.
Okay.
There's several people that helped me a lot, both with the comments and questions even, just asking questions, why I'm doing this way, maybe stupid way, but then I kind of start to think about that. But there is a lot of useful as well information like guiding and how to approach certain problems. I think that's the most important part is people on the course.
So the community.
Yes, the community and the guest stars as well that answer the questions, right? So that's
like Harold.
Harold was very useful for me.
Yeah. And would you recommend this course to someone else?
Yes, I did already multiple times
Okay.
to my friends. People are a bit afraid of analog, but at least a couple of my friends at least started digital. So
Okay. Cool. So, and you've actually, you're extremely well prepared for a feedback interview. You've even got some slides to show. So let's get them up and you can talk us through them. 0 to ASIC, analog edition.
So basically, I wanted to. Although, as I said, I'm kind of interested in neuromorphic part, but as well, I'm quite interested in retro stuff, trying to replicate. And I find some interesting kind of approaches that people did maybe in the 80s that I find useful for the neuromorphic design as well. And there is usually you have to do some digital to analog conversion and analog to digital. So like a simplest block I could think of first is to make a digital to analog converter, right? But it's kind of simple. I already had a digital design for it, like it's a sound processor from the back in the day, and I already had a digital design for it in one of the tiny tape outs, and I wanted to add a DAC to it. And it's a well-documented DAC. It's like the schematics are known. I know the exact inputs and outputs, and I have direct use to it. So I thought it should be easy. Then I looked at the schematics, and it seems very straightforward, right? It's basically just a parallel 16 transistors in parallel. Oh, sorry. So this DAC is a bit interesting. Is that it converts this kind of linear 16 values of the linear input into the exponential output. So that is not
it's a better match for the human hearing.
Exactly, it matches how we hear the higher.
Yeah, because if this was a linear DAC, then you would waste half of your resolution on stuff that your ear can't really even hear.
Exactly. And back in the day, they had like only 4 bits, right? That was super important. You can't really waste them. Now it's like you can have a lot of bits, so it's not a problem. And in the manual, they even had like oscilloscope. The result of measuring the chip on the oscilloscope.
Cool. I'm looking forward to testing this when we get it back. Which shuttle did it go on?
That went to 2 shuttles because I taped it out as separate design, and then I put it into the digital. So I think it was in 6 and 7.
Okay, so we can maybe check 6 soon then, because you've got the chips recently. Awesome.
Yes. So I remember, Matt, you were saying, pick the simple design. So don't do it. And I thought like, of course, 4 transistors, I cannot do it. It's just too simple, right? I have to do something like a bit bigger. And then I looked at the schematics, and it's like, it's super simple. I probably will be done like in 2 or 3 days. And it's just 16 transistors. So I thought it should be easy, right? It's cannot be hard. Then I kind of looked at the good thing as well with reproducing something that others did already. You can look how others solved this problem. So I took a decap of the actual chip back in the day. So it's like there are 3 DACs here, and they're on the top. And then if I zoom in, like this is 3 DACs from there, zoomed in. And this is actual part that I have to do here, basically close up. And on the right side is a decoder that decodes from the 4-bit to a 16 one hot kind of type, and then just controls those 16 transistors, or 15 transistors, sorry. And you can see they're kind of like there's a size. Each of them is sized different, and I thought at first it was not clear for me why they're like first going thinner and then going like broader, and I thought they should be all just like 16 every time, just bigger, but turns out they spray. So I thought it's probably for some reason, like they wanted to save some space. So I didn't pay attention too much to that at the beginning, but I knew how it kind of should look like. But yeah. So, and then basically the challenge was kind of simple. You just have to pick, because it's 16 transistors, you just have, and every transistor has to do like a different amount of current. And I know exactly the amount of current I have to get out. It's written in the specification. So basically the current is just, I have to figure out the width and length for the transistor. Should be easy. There's a table, and the table is like, I have a table from the book, 130 nanometer process. So the first thing people said on the Discord channel is like, well, actually the Sky 130 is not really 130. It's a bit something in between 180 and 130. It's like, take a look at those numbers. So I took those numbers, I put them in, and I made a simple schematic, and of course it was completely off. It was not even close to what I wanted it to be. I was kind of confused again, went to the community, to the channel, asked people, and they said, well, it's probably like something. So I started try to look at the models of the transistor. So I looked at the model of the transistor in the Sky 130, and then I see this like super complicated formulas with a bunch of numbers, that what they measured and how they work. So it turns out this kind of simple formula from the book doesn't really apply in reality if you make them small. If you make them very big, it's fine. But if they are small, then there is a bunch of like a secondary effects that kick in. So then I spent probably a week battling those secondary effects. I looked at the documentation, and it's like you can start noticing that depending on how width and length of those, like the ratio of them, they are completely non-linear in terms of how they output the current. So instead of doing my schematic, I started just playing with one transistor, just doing with them one by one and measuring them separately. Just and eventually I kind of just get a hold of how do I need to find a good kind of point around which I can scale them in different directions.
Yeah. So did you just pick like one width and then have different lengths to alter the current, or did you change both width and length?
I had to change both width and length, because if I pick one, that's what I thought at the beginning, right? If I pick one, and if I want to kind of do 16 of them, they just becomes way too long.
Okay, right. So you would have to have like the multi-fingered transistor or something. So instead you increase the width.
Yeah, so I in 8 of them I'm increasing length, and in 8 of them I'm increasing the height, and that is exactly. To be honest,
because when I'm looking at a transistor, I'm normally always looking at them like this, and then I'm seeing like the width, but that's not the width. That's the length. When people talk about the width of a transistor, they mean the length of the gate. I always still get confused about that.
I'm confused about that every time as well. It's like. So I think the naming is quite confusing.
Yeah. So these transistors, have you got a laser pointer?
I don't know if you can see
or your mouse. Yeah.
Can you see it?
Yeah. Yeah, I can see it. Yeah.
Yeah.
Yeah. So like there's like a kind of a triangle, like a set of gates in a row that form a kind of right angle triangle in the bottom left hand of the screen. Yeah, those. So those are all the same width. No, they're the same length, and they've all got different widths.
Exactly, they are same length, but have different.
So even though on the screen it looks like they're all the same width, but they all have different lengths. Yeah. All right.
So you can see that the contacts are like on the side of them.
Yeah.
Like a tiny ones. This is like those contacts.
Okay.
So so basically, and then you can see that there's essentially what I ended up doing the similar thing. Like you can one central one. Let's call this one in the center,
Mm-hmm.
right? So you pick the length so that you can increase length in one direction, and then you can go and increase width in another direction.
Okay.
So here it's a width, here it's a length, I think. So, and we can look at how. Sorry, if I jump, you can see this is
it's
my
very
way.
similar.
Yeah, it's kind of similar in a way.
They did have a good reason.
Exactly, and then it makes sense to put them like into this angle as well, because you want
it fits into a smaller block.
Yeah, it fits into a smaller box, and you want to get power and the ground from the different sides of them. So it's kind of it makes sense how you want to this layout kind of zigzagging pattern.
Cool.
I kind of knew the answer, right? So I put probably it would take me much more time if I would be doing that without looking at the original schematic to come up with. But quite a lot of became kind of natural while doing it.
I bet by the end you were like dreaming of this layout.
A bit, yes. It was. It was a surprisingly, satisfying game in a way where you have to think about that. It's like usually as a programmer, I'm like 1D, right? You write text, and here suddenly it's like a 2D.
Yeah, it becomes like a three-dimensional puzzle at the same time, where you're trying to recreate the thing that you go back to the X scheme. The simulation that you had, you got you end up with this test bench, everything looks good, you got your simulations, and then you have to move on to the point where you're actually got to do a layout that is going to give you the same thing.
Yes. So I was quite worried that what happens if my parasitics, when I do the parasitics extraction, it will be completely off the charts again. Luckily, it was very, very close. You can see that.
Yeah, it looks very close. Yeah.
Very close. Yeah. So I didn't have to redo it.
Cool. Okay.
And you can see that those steps are exponential steps.
Exponential, yeah. And I guess it's worth saying they're current DACs, aren't they? It's outputting it's a current that's changing, not the voltage.
Exactly.
You could put this across a resistor, and then the voltage would change.
Yes, exactly. It requires a resistor on the output to function.
Yeah, maybe a speaker or something.
Mm-hmm. It's as well. This is a metal layer on the bottom, and this is kind of the second. So I have two layers, basically 2 metal layers to wire everything up.
Yeah.
I went super conservative here, and I just use the transistors with the guard rings around each one. It's not necessary. It's actually probably too conservative. I just have to have one guard ring around them. So I have an idea how to optimize that, but I never actually went to read it.
To make it a little bit smaller.
Yeah, it can be done definitely smaller. Definitely, I don't need these guard rings and 2 layers together. It was. I mean, it kind of becomes a 3D puzzle. Yeah, not just 2D. It's a 3D. How do you kind of put those wires so they don't cross each other?
I can see that how that appeals for you as coming from the 3D graphics and the gaming background. Yeah. Have you ever thought about using one of these as the level for a game?
So recently with other things, yes, people were saying, "Oh, this looks like a game level."
Yeah.
I was rendering some in the Unity actually, some of those GDS files, and people were saying it could be a game. Yeah, it could be. It could be maybe even you can be useful actually, doing something like people like the collaborative design where you play the game and then you route the shortest.
Yeah, it's like a Tron, and where you drive is like leaving a metal layer behind you.
Exactly. I mean, it's you can make it simpler if you go 3 or 4 metal layers as well. It would be simpler, but I wanted kind of to make it closer to the original because they had very limited number.
Yeah, I guess those old school designs. When you look at one of these old wafers, you can put it under a microscope and you can see a huge amount of detail because they didn't have so many metal layers, so you can see the working. Also, they didn't seem to use fill so much, whereas now maybe fill is more important as you get like 7 or 8 layers because you have to keep the layers very parallel. So you add the fill to get the even density, so when you polish back the layer, it stays flat. Maybe if you're only going to do like 2 metal layers, it's less important and you don't need to do the fill. But the chips that we get back when we decap and image them, they're like the top metal layer is really boring because it's like the power distribution network, and then everything all in between all the wires is lots of tiny squares that you can't see through. Boring.
That's actually what Harold as well. And when I was asking, that's his suggestion. Like, yeah, just fill it on the top, right, and then just put the wires from the top down instead of trying to wire them here like I did. It's like just.
That's your retro roots calling to you. No, it has to be the same.
Exactly. Yes, it was.
Okay, so you did. You did. Yeah. This went on Tiny Tape at 6.
Maybe 7. I don't remember. That's the thing. I had one in the 6, one in the 7.
Okay.
So I need to check. I forgot before. So yeah, hopefully in the 6, so I can measure it. I still don't get. I think 6 is already somewhere. You have it, right? The 6.
I've got like the VIP edition.
Okay. But they're coming. I feel
they're coming soon. Yeah, in the next couple of weeks, you should get yours. Yeah.
So here I basically just wired all the inputs into the different input pins, so I can control it completely. There is no decoder or anything here, just like so that it would be as simple as possible design-wise.
Yeah, you can just drive it. You could like load a file into the RP2040 and then play out whatever you want. Yeah, it's definitely cooler than my DAC. My DAC was just the R2R DAC, super basic.
So actually interesting, in the later when they were upgrading the sim chips later on, when they kind of combined those, because when they were doing later game consoles, they would still use the same cores quite often for the newer designs, and then you can see that they're using the same core but a different DAC, and the new DAC is actually R2R.
Okay, maybe they just didn't do it because they take more space. Because like I was measuring my DAC yesterday, and it's an 8-bit DAC, and the steps are pretty small. The output waveforms are quite nice, but it did take up like 8 times more room than yours.
So, and those R2R DACs, when they do it for the exponential, they're quite weird as well, because they are not like not your usual ladder DAC, because they have to kind of size those resistors in a different way. So it's definitely complicated. But yeah, I think it was bigger as well. But it's probably in a way it is probably easier, because still, I mean, you just measure those resistors, but like otherwise it looks like a snake basically.
Yeah. Okay.
And the second tape out I took this digital logic that I had already, and instead of previously I would have actually like I had 8 outputs for the DAC, for the external DAC, or so I just took 4 bits and just wired them to the.
How come you needed 3? Is the A? Oh, I think I remember the AY8912 has actually got 3 different voices, right?
Exactly, yeah, 3 different voices, and they don't even mix them inside of the chip. They have 3 different pins.
Okay.
For that. So it was mixed externally.
Okay, so we should. And so does this? How do you control this with some like serial or SPI type interface?
So in this case, right, this is exactly as it was back in the day. So it's not serial or SPI. It's like it's 8-bit. It's an 8-bit kind of parallel port that you have to use. So
but you kind of to play this note starting here and then ending there over this amount of time, and then it just goes off and does this thing.
Yeah. So there are a bunch of this. Oh, sorry.
No, it's correct. Sorry, I'll stop interrupting you.
I think there's some delay. So, well, the VGM, there's like files that people capture from the original hardware. Like they just capture this 8 bits input pins and just store them in a file, so you can play them.
Okay.
Yeah, and yeah, so it can be with the Python. You can play them.
Yeah, cool. So we should be able to take some of these like classic chiptune soundtracks and just play them out. Yeah.
So Pat actually wrote this code already for me.
Oh, great. Yes. I did hear some more. Was that because he shared some really good sounding audio? Was that from one of your chips? Okay.
Yes.
One of the digital only ones?
Yes, exactly. Yeah, that was with the digital DAC.
Okay.
So the player is already there. So
and we know it works. Great. Yeah. Super cool. It's great to see these like mixed signal designs. It's really super satisfying. Like we've come a long way, I feel like, since we started. Yeah. Yeah.
Kind of the next step, what I want to do is, because here how I placed it, I think the same way you did. So I was just copying. I took it in the Magic. I opened the digital design. I put it in the Magic, and then I rooted it in the Magic. But now I would like to do it another way. Is like where you prepare a lib file, right? From my analog, make it into a macro essentially that I can put the digital design. So I don't need to open it in the Magic.
Oh, you think you could make it so that OpenLane could place it and route it?
Yes, exactly. Yeah.
Okay.
Yeah. Because the ROM, I mean, I look at how Sylvain is doing his ROMs, right? Because his ROM is a macro that I can place in the digital.
Yeah, you used that in the Atari 2600, didn't you?
Yes. Yeah.
Yeah.
His ROM is such an impressive.
Yes, and if you're interested in finding out more about the ROM, I will link Sylvain's video up there for you. Cool. Anything else to share?
There's a future works like this is those 3 guys zoomed in a little bit, and the future plan is, as I said, I want to make it cleaner. I want to optimize it, and op-amp. I want to do eventually an op-amp. And this is something I'm hoping one day
to save that for IHP.
DAC with the BGT transistors.
Cool. Okay. I look forward to seeing what you get up to in the future, and also to see the results of this chip. Hopefully it's going to work. That'll be a good addendum. Okay. Thank you.
And sound nice.
and sound nice, yeah. That's important for an audio DAC.